I want to show this question that I discussed last time related to simplex method, which was I thought it's interesting, and you guys should know that this type of questions can also come. Okay, so just take a look at it and tell me if you can solve this kind of minimization, and is there a trick to solving this? I will spend, I think, let's say 10 minutes on this. I have already solved it in the told you how to solve it in the previous lecture. So yeah, let's see if you can figure out the trick in this question. So what should be the first step? Anyone? So don't no need to worry about being wrong actually, because see, I myself did this question wrong. I told Pankaj also last class that while solving this question I tried 4 5 methods, and in the end I found out all were wrong, only one is correct. Okay, so you guys tell me yes and no. So when we are minimizing, or no, any problem, maxima or if we have been given, first step is to convert the problem into standard form, right?
Yes,
Yes.
sir.
Okay. So to convert this into standard form, it is already minimization, so we no need to do anything here. To convert this into standard form, we'll add a slack variable, correct? Add or remove a slack variable.
Add. Sorry,
It-
remove. We'll
Yeah.
have to
remove.
remove.
Yes. So okay. So we did that. So is this correct?
Yes, yes,
Correct, sir.
Okay. Now then we make the table, right?
yes, sir.
Okay. So we made the table. Now can anyone tell me which value is going to? So we made the table. We saw that x2 and x. We chose that x2 and x4 as basic variables, and these are the all variables that are okay. Maybe I have done. Just take. Let me, yeah. Let me just change this. We saw that x1 and x3 seems to be like basic variable, and then we made this table. Now who can tell me which variable is going to come in and which variable is going to go out? Just tell me which variable is going to come in. Okay, so let me tell you this thing. What was the rule? The rule was in a minimization, we already have minimization. So we choose the minimum negative coefficient variable, and that variable is going to come inside, right?
Yes,
Yes, sir.
But we don't see that here, no?
yeah.
So what do you think? This problem is wrong, or can we cannot do it?
It is already optimized, I guess.
Yeah, so that's the tricky part. It is not optimized. In such type of problems, we have to introduce artificial variables, and we have to make a new function that is a function of artificial variables. And in that function, we have, when we introduce the artificial variables here, x2 and x4, and this will be our new function that we are going to optimize. There we will have some negative, and we are first going to optimize this. So this will be the new table. So we are first going to optimize this variable, this AF function, and after we optimize that, we will remove the AF function and its this artificial variables, and then we will see whether we can optimize F. So that's the step to do it, and this is the answer that you will get after optimization. So you guys can see the past week video. So in that I have not solved it. I have shared the Excel sheet where I have solved this along with these. These are also there in PPT, but I have shared the Excel sheet where step by step we have solved this. And some examples also. So you can check that and you can see how we are getting to this thing. Okay. Now we'll go to this week's content. Okay, so today we'll be discussing some problems based on interval halving method, golden ratio, bisection, and Newton-Raphson. We'll discuss one problem and we'll solve it. Maybe two problems if we have time, and we'll solve it by each method. Okay, so before we solve, there is in the PPT that sir shared, this was one of the questions, right? So if we have a and b boundary, if we have fx like this and we have a and b boundary, and x1 and x2 are some variables that somehow we got either by golden ratio or interval halving, and this is the case that fx1 is greater than fx2, then which region is eliminated? So everyone agrees that this cross region is eliminated.
Yes, sir.
Okay, so
Yes.
yeah, very good. So now my question is, I see that the this region also doesn't have the optima. So why can't I remove this region?
Actually, f of x1 has been finalized, is greater than f of x2.
Yes,
So it is sure that that side is having the greater value
yes, correct.
from that statement.
No, but what about this one? We are not sure
Sir,
about this side.
you need to define the unimodal function for that reason.
Okay, so we have to define the unimodal function. No,
F of B, that means f of B is greater than f of x2, then that reason will be eliminated.
no, actually, not necessarily. There is a simple way to do that. Simple way to justify that why can't we remove this region. Okay, let me show you that. So this looks a symmetric unimodal function, no? What if the function is like this and our x1 and x2 are like this? Here also f of b is greater than f of x2, but if we were to remove this, we will lose the optima also, right?
Yes,
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 yes, sir.
So because we were not sure where is x2, whether it is before optima, after optima, so that's why we did not remove this region. Only this region we have removed because we know f x2 is lower than x1 and it is a unimodal function, so means it is going to and here it is going to increase only. So yeah, your justification for removing this is correct, but something to help us, you know, solidify that why can't we remove this particular region.
Yes, sir. Yes, sir.
Okay.
yes, sir. We are not sure ki where the x2 lying.
Yes.
Hmm.
Perfect. Okay. Now here is the table for these conditions: interval halving and golden for minima. We will let's all of us try to get this using these examples. So I would suggest that you guys open your Excel sheet if you have a system at hand, because I'm going to solve these problems in Excel sheet. Okay, so we will get this. This is for your reference. I will not look at this. Maybe I will look at it if I am getting confused. But we will solve this problem and we'll set these boundaries based on our own observations. Okay. So let's start. I will share the Excel. So we have a function. You can write it or you can make it Excel. Open an Excel, whatever you wish. So this is a function. Let's start with interval halving method. Okay, so let's just let me zoom in because last time there was a problem for you guys to see my screen. Is this one fine?
Fine, sir.
Okay, okay, let me just, I didn't paste it. Okay, it seems it's not going to Let me copy paste. So the function was 2x cube minus 3x square minus 12x plus 4. 2x cube minus 3 square minus 12x. Okay, and I have given my a as 0 and b as 3, right? Yeah, given a as 0, b as 3. Okay, so let me write xm for interval halving method. Let me just name this sheet here. Yeah, name this sheet here. Interval halving. What is xm? It is nothing but middle of these two. Is this correct?
Yes.
And x1 and
2
x.
cube minus 2x square.
Oh, okay, okay. Thanks. So yeah, this was a 3x square here. Thanks, Pankaj pointed out this. And what is x1? X1, so we have divided it into equal parts, right? So we have, let me just draw this also. It will be beneficial for us when we are deciding the condition. So we had divided this particular thing into equal parts. So this was xm and this is x1. X1 is middle of a. Okay, sorry. Middle of a
And
and xm, and x2 is middle of a and x, uh, middle of, sorry,
XM and
xm and b, right? So let's do that. It is sum this plus this 12 by 2. Is this correct? Yes or no would suffice.
Yes.
Yeah, okay, thanks. Yeah, so if x1 x, oh sorry, fxm and fx2. So what is this? It is 2 into this q minus 3 into this square minus 12 into this plus 4. This is correct, right? Yeah, it seems correct to me.
Yes, sir.
Okay. Now what we do is we just drag it. Sorry. No, that is not. Okay. We just drag it and it is going to calculate for the other two. So fxm is going to take the xm and fx2 is going to take the x2. You guys are familiar with this functionality of Excel, right?
Yes.
Okay. Now we have our condition. So let me go to the power, this paint, and we will sort out our condition. So this was x1 and x2. So in this particular case, what do we see? We see that fx1 and fx2 both are greater than fxm, right?
yes,
So what will be our approach? What will be the new value of a? Will it be x2?
new value of A will be x1,
Yes. New value of a will be x1 and new value of b will be?
x2.
Yes. So we eliminated this region. Okay. Now my question is, can I make a new one? Yeah, I can make a new one. So let's say this is our first condition. So if fxm, let me write it here also. Let me write here that we will put here in this particular thing, we will put 1 if, okay, let just 1 minute. Yeah, in this particular sheet, cell, we will put 1 if our f(xm) is less than f(x1) and f(xm) is less than f(x2). Okay, so this is what we will do if that is the case. Let me minimize these things so that we have some more space. Yeah, this will be the first condition. Second condition, yeah, I will not draw A and B. Let me, for to easily fix this thing, let me draw this. This is x1, this is xm, and this is x2. Okay, so this is m, this is 2, this is 1. Now what do we see here? We see that fxm is greater than fx1 and it is less than fx2. Okay, so now what do you guys think, which region should be eliminated?
Between m and 2.
No, actually,
Yes.
okay, so I didn't draw the A and B. Let me draw the A and B. Now we tell which region should be eliminated.
B and M. Between B and M.
B and M or B and 2? So what will be the new B, you tell me? What will be the new B?
Yes. New B will be 2.
Yes, so we have eliminated this particular region, right? This region we have eliminated because this is our new B. And A?
Will
What?
remain same.
A will remain same. Is it fine with everyone? So why A will remain same is again the same thing, because we don't know whether this 1 x1 is here or is it here, right? So we cannot remove this particular A. We cannot shift it. Otherwise, if we shift this to here, we had shifted, then we will lose the optima. Correct?
Yes.
So what we saw here, our condition is that if fx2 is greater than fxm, then we change B. So that will be another condition. Similarly, we will have another third condition, that if fx1 is greater than fxm, then we will change A. So let me write here also, change B, change A. So we will use now the power of Excel to solve this very easily, this problem. Yeah, so here actually it should not be modulus, it should be normal sum only, because if our interval is in negative, this modulus, if you use here modulus, it is going to push the root into the positive. So you use here this thing only. Yeah, so okay, so how many people are aware of how to use if and else in the Excel?
Where aware.
Okay, anyone not aware? Okay, I assume that then you are aware. So let me write here, and if you have doubt, then you can, or if I do something wrong, then people who are aware can point it out. So I'm writing the function here. Okay, how do I increase this size? Anyone knows how to increase this size? Okay,
There's
wait.
an option bottom right of your screen.
Bottom right.
I think that one.
No, this went something else.
No,
Okay,
sorry, slide the slider.
yeah, I will write it here itself, and later on I will make everything fine. Okay. Doesn't look okay. Yeah, let me write it here. Okay, so now if our xm, okay, sorry, yeah. So if so I think when you said you are aware, then you must be knowing that if we have to compare two conditions, then we have to write and inside that we have to write both the conditions, right? So I'm going to write my condition one, that my xm is less than this and this. So if xm is less than this, then comma for the other condition, then fxm is less than this. If both these are met, then I am going to return 1 according to this. And now else, now we have to write else. So again I write if xm is greater, sorry, x2, right? If x2 is greater than xm, return 2. So, and then our third condition, that is if x1 is greater than xm, return 3, and return 0 if none of these are met. Okay, it seems I have, okay, sorry, I should not have put here. So it says that condition 3 is met. Is that correct? Condition 3 is if x1 is greater than xm. It seems correct, right?
Yes.
Okay, now let's write here absolute of this minus this. And this is just the middle of this and this. Okay. We have made our, yes, Pankaj, you wanted to say something?
Yes, the condition is not clear.
Which condition? How I
Column
made this
L.
if loop or the condition itself?
Yes. Yes. This here, how we are writing.
How we are writing the if?
Yes.
Okay, so see, if is basically is it we have to check if whatever is our, so here you will also see in the excel when you are giving in the excel. So first is the logical test
Hmm.
that we have to do. So we are doing the test here, that is
Yeah.
whether these two conditions are met or not. We have put and here, that means both the conditions should be met, that is xm should be less than this and this, then it will return 1. Okay, till here is it clear?
Okay.
Then this is going to be our
Okay. Yes, sir.
else. Yeah, tell me. Yeah, Pankaj, you
Nothing,
can.
sir.
Oh, okay. Yeah, so this is our first logical test, that both this and this are met. So for that we have to write them inside the and if they are met, the logical test is passed, then it is going to return 1, because that's what we want. And if it fails, then it has to go here. So if that is not true, then we are going to again check whether it is the second one true, is the second condition met or the third condition met. So uh, inside the statement where we return false value when the condition is not met, I am going and checking again, okay, this is not met. Then you check whether x2 fx2 is greater than fxm. So that's what I am checking here, whether fx2 is greater than fxm. Then you return 2. Then if this is also not met, then you check if fx1 is greater than fxm, then you return 3. And then in the end, I have to return if all these 3 are not met, what I should return, what I should get. So I just put a random value, you can put anything. I put 0 here. And then we close the bracket.
Okay, sir.
Excuse.
Yeah, Jesuri.
Sir, is it necessary to evaluate the conditions in the same order?
No, not at all.
Okay.
Yeah. So, okay, so now condition 3 is met. So when condition 3 is met, we decided we will change the A, right? So let me write it here. So when do you guys think A is going to change? Which all conditions will make the A change? Like whether condition value 1, 2, 3, what are all the values when we have to change A?
1 and 3.
1 and 3, right? Yes. 1 or 3, sorry. So that's what we'll do. We'll do is equal to if and then or, means any of, if it is either 1 or 3, we have to change A. So that's what we'll do. If condition is equal to 1 or condition is equal to 3, then our A is going to be x1, otherwise it is going to remain same. Is correct?
Yes,
Yes, sir.
yes.
Okay. Now we do go here is equal to if or this is equal to 2 or this is equal to 3. Oh, sorry, 1. If this is met, then B will be x2, otherwise it will remain same. Yes, Manohar, you wanted to say something?
No, no.
Okay.
It is correct, sir.
Okay. Now I will just select all these and drag them down. Okay, so this is our second iteration. And when the concept is clear, I will just keep on dragging this down and we'll get our answer 1.988. 1.998. So the answer, it's going to 2, and that is the correct answer. And here you can see conditions are changing on their own. So sometimes it is 1, sometimes it is 3. So is it clear? Everyone is kind of understanding how to do this?
Yes.
Yes, sir.
Yes.
Okay. So we have solved this problem using interval halving method. Now let's go and solve using the golden ratio method. So let me see if I can copy and paste this into a new sheet. Is this fine or should I zoom more? Uh,
That's fine, sir.
it's fine?
Fine.
Okay. So if it is not fine, then you will lose the live interaction. I don't know. I will just zoom it a little bit more. And if
No,
even
it's
if you,
okay.
okay. So okay, so we have in our golden ratio method. Let me just name it golden ratio. The sheet I have named. Okay. Okay, I have already named one. Okay, now let's give me underscore. Yeah. In golden ratio, we have to divide it into 3 parts. The search domain by x1 and x2, and then we have our fx1 and have our fx2. Then again we have to check for condition, and we have to then give this check the width of the remaining domain, and we give our middle of the domain, search domain, as the answer in the end. Okay, so now let's go and Okay, yeah. So tell me, I think you must be knowing if you have attended the class. When is the golden ratio such method better than interval halving method? What value of tau? Oh, Jesuri, you have raised your hand. You can unmute and ask.
No, sir, I haven't. It must be a mistake. I'm sorry.
Okay. Okay. Yeah, so it's just like kind of a MCQ that can come into your exam. That what is the value of tau that you choose when you are at which this golden ratio is better than interval halving method?
Is it 0.618?
Yeah, 0.61. Very good. Okay, so let me draw once. I probably may be doing a little bit different than what Rito has done. So this is A and B, and this is x1 for me, and this is x2 for me. Yeah, A, B, x1, x2. So how I write x1 is, it is A plus 1 minus tau into the L, and L is nothing but this whole thing. And how I write x2 is B minus 1 minus tau into L. So is this clear? So this is what notation I am going to use, because if I change, maybe I'll get confused in the solution process. So is this acceptable to everyone?
Yes, sir.
Okay. So let me just put the values in the Excel sheet. So actually you can change. I want you to be able to change the value of tau and at the same time get what what is the efficiency of this golden ratio. So I will keep a tau here and we'll use that value everywhere. So x1 is this plus 1 minus tau into, let me just give here, I don't want to compute again, and x2 is equal to b minus 1 minus tau into this. Okay, so for it to always choose this for this thing, even if I drag down, I have to put a dollar. I hope you are familiar with this, because when we drag down, Excel has a habit to drag down the this also where we are referring to.
Yes, sir. Yes.
Yeah, so we have to put a dollar here for which for the cell we want to fix. So I have fixed here for the x1 and x2 so that it keeps the same tau. So let's just get over with this a minus b. So now we got our x1 and x2. Okay. Now let's calculate our fx1 and fx2 and then see which region we have to eliminate. 2 into 2 minus 3 into square minus 12 into. Is this correct? That seems correct. Yeah. And just I drag it to this side and I get the value. So what we see here is that our fx1 is greater than fx2. So there will be two conditions. We will name the condition 1 when fx1 is greater than fx2, and we'll put here 2 if fx2 is greater than fx1. And after checking in the paint, let's decide which value we want to uh, update when a condition is met. Okay, so let me remove x2 because they are looking very much similar here. Let me change the position of x2 from that place to this place. So here we see that fx1 is greater than fx2. So what do you guys think, which region should I eliminate?
A to x1.
A to x1. Perfect. Anyone has any objections? Okay, I will take it as a no because this is the right answer. So I will remove this region. Why will I not remove this region, this particular region? Because I know that we don't know whether x1 is uh, on the left side of optima or it is on the right side of optima. So we are going to update our A, and A is the arrow. Okay, yeah. A is going to be x1 and B will remain as it is. And similarly, if our x2 was greater than, if our x2 was suppose here, it will be greater than x1, then B will be changed. But in this case, that is not happening. So now we have decided, we have figured out this particular condition. Let's write the if loop again. So I am writing the if. Maybe Pankaj, if you are not clear for the first time, you can get clear as we go on. So is equal to,
Okay, sir.
yeah, is equal to if x1 is greater than x2, our logical test, then I will give 1, else, now I will write again, else I will check one more time if, maybe I don't need to check, right? Yeah, I don't need to check. Otherwise
You
I
can
will,
directly write the
yeah,
values.
otherwise else I will return 2. This correct, right?
Yes, sir.
Yeah, so this particular case condition 1 is met. Now I'll write here is equal to, if here it is condition 1, so what did we see? We have to change A, right? Change A. Let me write it here. Change B. Ah, shit. Change B. So if our this condition is 1, then you change our A to x1, else you keep our A same as previous. And here we write if this is 2, then you change our B to x2, else you keep the B as old B. Now our A and B is fine. I just drag this down. So this is our first iteration is done. Now we can just drag the whole thing down and we can see that it is kind of oscillating around 2. So that is one of the problems that you can see in these interval methods, that it may oscillate, but eventually it is going to come to 2. Yeah, so as you see, the oscillations are reducing and eventually it is going to come to 2.
Yes.
Is it? And you can see here the conditions are changing, 1 2 1 2, like that it is changing. So is the golden ratio clear?
Yes, sir.
Okay.
Yes, sir.
Okay. Now let's go and solve this using interval halving method. No, sorry, bisection method. I said interval halving. A, B, bisection method. I like the bisection method because we don't have to do, not many variables are involved in this thing. Okay, so is anyone motivated enough to differentiate this and tell me the differentiation?
Yes. 6x square
Yes.
minus 6x
Okay.
minus 12.
Perfect. Yes, this is the differentiation. So we are going to use the differentiation in case of bisection method. And xm. And one more thing that I like to do here is this thing that you would have seen sir mentioning that fx, if f dash x is less than 0, then you change a, if you f dash x is greater than 0, then change b. But what I like to do is I like to check the sign of uh, f dash at a and b, and then compare it with f dash at xm, because in that case I can use actually the same thing for maximization problem also. I don't have to stress too much about maximization. I will just show in 1 minute. Let me just finish this. So yeah, let me come to this thing. So we have a thing, and this is our a, this is our b. What actually it was meant in the class was, so the tangent of, okay, tangent of this particular function at a, what will be the sign of the tangent? Can anyone tell me at this point?
Is it negative?
Negative, correct, because it is decreasing. At this point we can see the function is decreasing, so it is going to be negative. And at this point the function is increasing, so the sign will be
Positive.
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 Yeah, so it is positive here and it is negative here. So it is not always true that whenever it is negative we are changing the a to xm, and whenever it is positive we are changing b to xm. We are actually checking that at xm what is the sign of this derivative. So if it is negative, then we change whatever boundary is having the same sign. And if let's say our xm was here and it was positive, then we would see, okay, b is having the differentiation positive, so we'll shift the b to here. Is it clear? So we'll use that technique to solve it. Okay.
Yes, sir.
So yeah, that's why I like to calculate f dash a and b. So it was 0 and 3, and it is just the middle point of these two, and f dash a is going to be 6 into this square minus 6 into this, 12. And then I just drag it. Oh, I didn't put the condition. Okay, my apologies. I will just insert here one. Uh, yes, Purvika, you wanted to say something? Okay, Purvika left. I think she is having problem with the internet. Okay, yeah. So we have our condition. So what was the condition? Condition was if is equal to if. So how do we check the sign, whether the two things have same sign? What do you guys suggest? How should I check?
Less than 0, greater than 0 should be fine.
Less than 0, greater than 0. What should be less than 0 or greater than 0?
F dash of xm.
Yeah, no, I am saying I want to compare their sign. I don't want to see whether it is less than 0 and it is less than 0. So I said, no, here what we will do is we'll calculate the f dash xm, and we'll check whether its sign is matching with f dash a or f dash b. Whichever f dash a or b it is matching sign with, we will replace that particular value with xm. So how do you suppose we check whether this f dash xm has same sign as f dash a or f dash b? I think it is too simple, but I am not able to explain. Let me just write here. It should return 1 if uh, f dash xm. You tell me if I, after writing this, if you are able to see that this is correct. Into f dash x, oh sorry, a. Now do you understand?
Yes, sir.
So yeah, so return when f dash xm and f dash a have the same sign, then this is
Should
going to
return
be
positive.
greater than 0, correct. And then here we change a. Okay, and I just copy this here. Return 2 if it is having same sign as f dash b. So we'll change b. So let's write it here. Is equal to if our logical test, that is this multiplied by this, is greater than 0, then return 1. Otherwise, so there is no other possibility, right? So I just we just do this. It will mean that it is going to match the other side because it is UD model. So I am just going to
Yes.
give here 2. So now we have this. Now we just write it here, a minus b. We have this and is equal to, okay. Now I just again check, okay, if the condition is 1, then I change b a, if condition is 2, I change b. If this particular condition is 1, then a value is going to be xm, otherwise a value is remaining same. For this is equal to, if this condition is 2, then b value is going to become xm, otherwise p value is going to remain same. Now I just select all this and drop down. So this is my first iteration. Now I can just drop down all the things and I can see that it is again, as you can see, it is slightly oscillating around 2, but as you go deeper and deeper or more iterations, you will see that the magnitude of the oscillations or the domain, such domain, is decreasing. So our final answer, it is approaching 2. So is this clear, the bisection method?
Yes.
Okay. Now, yeah, now so our main TA Chandra also has joined. So welcome, Chandra. Yeah, so let me just write it here, bisection method. Now let's solve this problem using our Newton-Raphson method. So we'll need fx, f dash x also. Just let me just copy this itself here. So who is motivated enough to tell me what is f double dash x?
12x minus 6.
Yeah, perfect. Lx minus 6. Okay. So one thing I would like to say, we are all learning all these methods, golden bisection. We have seen no interval halving, golden ratio, bisection. But most of the time, we end up using this. I personally have used this in Newton-Raphson because it is much more faster, as you might have also seen, or your professors also might have told you. But there are some cases where this Newton-Raphson fails. So, what is that case? Can you tell me?
Then f double dash x is 0 at x.
Yes. So, when we are talking about a optima point, then the Newton-Raphson fails when f double dash x is 0. And what about when we are trying to find the root? Then when does this f dash x? No, sorry. When does this Newton-Raphson fails? Okay. So, okay. Let me just write this. Maybe you guys have forgotten, probably. Oh, no, sorry. Yeah. So x n plus 1 is equal to x n minus f dash x divided by f double dash x. So this x and this approach is going towards what? It is going to give us a root, or it is going to give us optima?
Root.
Are you sure?
Yes, sir. Yes, x is the value of root, right?
Okay, so what is okay, let me just again using a figure, maybe it will be better to explain. Oh, yeah, I can just make a new one, right? Yeah, okay, so let me draw axis. Am I able to change this? No. Fine, okay, so what is a root here? What do we understand by root? This is the root, right?
Yes.
So root means when fx is 0. And what about optima?
F dash x is 0.
F dash x is 0. So it will be not necessarily there. I will use this. Let's say this is our function. So when you want to find out root, so actually this was not correct. So whatever you see this, a little bit maybe a trick or something, whatever is in the numerator of this part, no, that is going to become 0 in the Newton-Raphson method. Okay, so now
Okay.
after seeing this, you tell me this is going to give us which value? Is it going to give root or optima?
Optimum.
Optima, right? So I will just write it, so as a visual memory it will be stored, that xn plus 1 is equal to xn minus f of x divided by f dash x. So this will be for the root, and for optima it will be same thing here, minus
F dash.
f dash x, yes, divided by f double dash x. So let me just write it nicely so that, okay, so that's the thing. And what are we trying to find out here in our problem? Okay, so Jesuri I think got bored, so he has left. Oh, he, welcome back,
Sorry,
Jesuri.
sir. It was a
No,
mistake.
no problem, no problem. So we are actually trying to find optima.
Optima.
So we are going to use this. That's why we need a f double dash x. So let's make an initial guess. I told that we have a as 0 and b as 3. So let me take the initial guess of x naught or xn as the middle value 1.5. Then what I write, I will write f dash of x is going to equal to 6 into this square minus 6 into x minus 12. Is it correct?
Yes.
Yeah. We have f double dash x, that is equal to 12 into xn minus 6. It is pretty straightforward. We have this, and x f of no xn plus 1 is going to be xn minus this divided by,
F dash x by f double dash x.
perfect, yes. And then our new xn is going to be the previous xn plus 1. So I just drag this again here. This is our first iteration done. Now I drag the whole thing, numerous iterations, and you can see we have made our f dash x as 0 in, I think, fifth iteration. Yeah, it is pretty fast. I don't need these values. We have made our f dash x is 0, and we got that x equal to 2 is the value for this optima. Now let me, can we check this? Let me just also see if we can get the value of root also. Can we get a root also? So, okay, so what do we need for root?
Just f of x and f dash x.
Yes. So, and the root formula is?
Xn minus f of x by f dash x.
Yes, perfect. This is our root formula. What I can do, I can just copy this and paste this here, and I can see which value it is taking, and I can drag the cell to this. You guys are familiar with this, right? You can copy and drag the cell which is it is going to use. So I don't have to write this equation again. So yeah, so 1.5. Now for fx I will have to write because I didn't write it previously. So it is 2x cube minus 3x square minus 12x plus 4. Okay, and xn plus 1. Simply we are the above equation that we have written, xn minus fx divided by f dash x, and the new xn is going to be the previous n xn plus 1, and we can just drag down this thing. Oh. And you can drag down the whole thing to see that it has given fx is equal to 0. So that means this is the root, that is 0.313859. Okay. Yeah, so I think we are at time also, and I have discussed what for the first time I have been able to finish what I wanted to discuss in the class. Yeah, but there is a problem for you guys that you may, if you want to try, you can try using the same problem in a different region. You will see actually when you plot this function in Google or anywhere in MATLAB, you will see that it is this function looks like this. Yeah, like this, something like this. Maybe this. Let me make a new. Don't save. Yeah, something like this it looks. So some region we will have our maxima, some region will have our minima, something like that. So I have given a different region here to choose the optimum maxima. So you can again, as we have discussed in today's session, by drawing the plots and checking which region should be eliminated, because these things that I have shown here or shared here, is it? Yeah, this is valid for minima. So you might have to change these conditions for maxima. So I will suggest, if you want to try, you can get this and check. And basically in Newton-Raphson, there's one more thing what I like about Newton-Raphson is, let's see. So here, okay, here we had our region from 0 to 3. I chose as 1.5, and we got a optima, right? In
Yes.
Newton-Raphson, there's no need to worry about this thing. Actually, you want to find a maxima, then you select a point in between this region. That's a good thing about Newton-Raphson. So instead of xn of 1.5, let's say if I select an xn of -1, then you will see that it is going to give us a different optima. Oh, I think -1 was the optima. So let me let me select -1.5. So you will see that -1 is the different optima where it is going to be maximum. So you can check and try to do this using the bisection, interval halving, golden ratio methods. These things will change a little bit, but you can easily identify that by drawing this particular curve and then checking where your x1 is and x2 is. Okay. So yeah, that's all for today's session. Did everyone understand what we learned today? What I tried to explain?
Yes, sir.
Okay. So then I will end the session if for today. Thanks everyone for sticking.
Th-
Yeah.
Thank you, sir.
Thank you. Yeah. Bye.